let's get started. Yeah, I'm all good to go. Manisa, please feel free.
Thank you. Thank you. And thank you everybody for to join today's event. We're very happy to have all you here. If you decide to join today's event, it's probably because you love data science, you're interested in it. Maybe you're working in the data science industry. Maybe you want to work in the data science industry. And we welcome all of you for today's event. As Vivian have mentioned, my name is Monisa Felsen, and I'm actually, oops, not this. I'm actually one of the admissions officers here in the school. And before we start today's event, I promise I won't take much of your time. I just want to talk a little bit about us. Probably at this point, you guys are seeing my screen. And let's talk about who we are. And we are a data science school. We provide accelerated data science training for all students that are considering, either get better with their data science skills, or maybe, going for a career transition and start a new job in data science. We are very proud to say we are the only boot camp that teaches two programming languages that are very important for data science, both Python and R. Also, we are proud to allow our students to work with projects that, are hands-on and allows them the opportunity to experience, at the industry level. Well, we also assist all our students, our graduates with job placement. And we are very experienced in doing that, guiding you what's the best way for you to put your resume out there in the job market and how to navigate in the data science job market. We've been doing this for many students. As you can see here, we've been, helping over 2,000 alumni, and we keep counting. And well, not to brag, we were rated the best data science bootcamp and best online data science bootcamp by switchup.org in 2020. If you are interested in our boot camps, if you're interested in our data science boot camps, you can actually contact us. And admissions is happy to schedule a call with everybody and give you more details about our start dates. We have a start date starting May 3rd for remote live bootcamp. And then if you're interested in part-time and keeping your job, we have a start date in May 17th. And then early in the summer, we also have a start date July 6th. All these start dates that I'm mentioning, we're also offering a 10% discount. So if you have more questions, feel free to send your message here for me on the chat, or send an email to admissions@NYC Data Science Academy. Thank you, everybody.
Manisa, where can they find the link to apply, and where can they find the dates?
I will send them the information in the chat below.
Okay, great. Thank you. Cool. Yeah, Luke, feel free to get started. And I'm putting the downloading file into a Dropbox, and I'm gonna share the link soon.
Thank you, Vivian, and thanks for Manisa to introduce our school. And as Vivian mentioned before, my name is Luke Lin. I'm one of the data science instructor here in NYC Data Science Academy. Before I joined the company, I was a PhD student in math, and then I switched my career path from pure science to data science with more application. So a while ago, Vivian asked me to come up with a topic to share with, more public audience that kind of illustrate the way we talk about data science, the philosophy of our teaching. So I was thinking, what kind of topic that we cover in the bootcamp is, easy to share with public with different kind of background. So if you have looked at the link that Vivian just shared with you, if you got a chance to do so, I decided that I would like to talk about something called likelihood function. Allow me to share my screen with you. All right, so this is actually the GitHub page of this tiny project. And if you download the folder Vivian just shared with us in the chat, you will see the readme.md. And if you just open it with if you're familiar with say RStudio or other editor, that would be great. Otherwise, just any text editing software, you should be able to open it here. You'll see that the title for the talk I like to give today is how strong is your machine learning model? But really what I want to talk about is likelihood function. And why do I want to do that? Why did I choose this likelihood function as my topic? First of all, because it is everywhere. It is everywhere. One of the most popular topic or technical tools that people develop in the data science community is so-called the classification algorithm. So you would like to let the machine to differentiate or predict the class for you. For example, if you have a transaction data, you want the machine learning algorithm to tell whether it is a fraud or not, whether it is likely to be a fraud or not, right? So either it is a fraud or it is not, true or false. That's a differentiating discrete values in a sense. So that's a classification problem. And it could be as complicated as if you just feed an image to a machine learning algorithm and the algorithm will tell you what it is. It might tell you, hey, this is a clothes, this is a car, this is a dog, this is a cat, right? That's also, it's not a numerical value, it's not a continuous value, it's discrete values. So that's a classification problem, which is very, very important with wide application. And I would say one concept that stands in the core of this classification problem is really this likelihood function. So if your classification algorithm is designed to differentiate two different kind of object or two different classes, true or false, right, positive or negative, fraud or not fraud, that's a so-called binary classification problem. And to implement binary classification problem, or to evaluate a binary classification problem, no matter what the purpose is, people very often use this likelihood function to decide whether your classification algorithm is doing good or not. Okay. You could start from probably the simplest classification algorithm, the logistic regression, all the way to a very complicated neural network. But the so-called objective function will still be the likelihood function. So this is really just a very, very popular, widely used function or concept in the data science field. Yet it's also something that we got most complaint from the students, saying that the math is complicated, it's not easy to understand, it's very abstract. And I'm sorry, because personally my background is math. I got a PhD in math department. So when I first learned this likelihood function, it's really just another function that I encountered. So when I started teaching in the academy, when I encountered a question from students saying, hey, I don't really understand this likelihood function, I started to think, how can I explain this better, right? Is there any way we could connect these kind of abstract mathematical concept with our everyday experience? Was there any question? Okay. Because personally, I believe in what Einstein tells us, the whole of science is nothing more than a refinement of everyday thinking. Because of that, I share this with our students a lot, especially in the graduation ceremony. I do see some of our students here. They might have heard me talk about this. So really, there is no magic in science. Whatever we do as a scientific tools or technology, there must be a root somewhere. So I try to do that. I try to explain I would like to explain this likelihood function in the context of classification problem. Okay, so I will give you an example where we really want to make a prediction of two possible cases. Right? It could go this way or that way based on the data, which way it's more likely. And then once we make our prediction, I'm going to show you how likelihood function can help us to decide whether our prediction is good or not. That's the example I'm going to show you eventually. But before that, I do want to motivate the idea of likelihood function with something that probably all of us are familiar with, right? Flipping a coin. So a typical question that we probably have learned to answer when we were in high school, even middle school, is if we are flipping a fair coin. And what does it mean by fair coin? Well, a fair coin is a coin has two sides, either the head or the tail, right? A fair coin is a coin that, if you flip that kind of a coin, it's equally likely to get a head or a tail. So you have a 50% probability to end up with a head, or a 50% probability to end up with a tail. You know one, you would know the other. Excuse me. A typical question we would like to answer is, well, suppose we know that we are flipping a fair coin. What is the probability that we end up with a head, a tail, and another head? So this little question, can people help me with in either the chat or feel free to unmute yourself to give me your answer. Any idea? Or how do we compute it?
Is it 12.5%?
12.5. Thank you. I also see that in the chat. And
Yeah.
How did you get that?
I did 0.5 cubed because there's a
0.5
50%
cubed.
probability of each instance. So it's an intersection of 3 events with a 50% probability each.
Exactly. So once we know the probability of individual event, then the probability of all of them happen is really the product of the individual probability under what kind of condition? So there is actually please.
Is it independence?
Independence condition. Thank you very much. So if you're not very familiar with these kind of statistical concepts, this is okay. But the thing is, independence condition is a pretty natural concept that when we flip the first coin, it doesn't tell us anything about the second flipping or the third flipping, right? So these flipping are independent. If they are not, let's consider a very extreme case that if they are identical, there's certain relation among three. Say if you got the head at the first, then you will get the head at the second and the third flipping. That's a very strict condition, which is not natural at all, right? But if that kind of relationship exists, then the probability you got head, tail, head is 0. It's no longer 50 times 50 times 50. So that's an independent condition which is assumed widely. With this independence assumption, we can derive the probability based on the assumption of the probability of individual event. We could derive the probability of the overall, all of them happen. In a sense, this, I call it assumption before, but very often it is, or in the context of a classification problem, more commonly people would treat this as our model. A model will give you the probability of individual event. So if you change your assumption, essentially you change your event. I'm sorry, you change your model, okay? So let's say for some reason, the coin that we are flipping right now is not a fair coin. for whatever reason, probably it's heavier on one side and the shape is not very symmetric for whatever reason, okay, the probability we got ahead is 60%. And so that the probability we got a tail is 1 minus 0.6 equals 0.4. Okay? And if that's our assumption or our model, then the probability that we end up with a head, a tail, and another head will become, again, assuming the independence condition, it will be 60 times 40 times 60, which is 14.4%. Okay, so if you change your prediction on individual event, it's going to change your overall probability. I want to make sure, first of all, it's clear what the relationship among these numbers. We have the assumption on the individual flipping, and then we would like to compute the probability that all these events happens together. Any question about the discussion so far? All right. If not, I would like to take a little bit different perspective on this question. When we were in a high school, middle school, it's really a very simple probability questions, right? But if you kind of change the way we look at this and think about the context of the classification problem, our assumption, as I mentioned before, that 60-40 assumption or 50-50 assumption, that's actually our model. Okay, later when I talk about the logistic regression model, you'll kind of see that what does the model classification algorithm, what does it do? Well, the main goal or objective of a classification algorithm is to give you the probability of individual event. It will give you the probability of how likely something happens. How likely something happens, okay? And then what we see here, the outcome here, the outcome that we try to derive the probability, that is the data. That's a reality. That's a reality. We probably don't know the real probability behind, flipping a coin, but we end up with a head, a tail, and another head. So this is our data. This is our data. So for other kind of a classification problem, we probably don't know the mechanism behind, fraud or not fraud, positive or negative, but we could go ahead, collect the data so that we have a sequence of fraud, not fraud, something like that. And we might, collect a data set that got positive, and negative. So we have, so the outcome that we got from the data set, that's the fact. That's the data. And we try to use our assumption or our model. We try to use our model to describe or to explain the fact that we see. Right? So now, in a sense, we have two explanations. One is we have a fair coin. The other is we have a 60-40 coin. Let me just call it 60-40 coin. So can people kind of guess which one is a better model in this case, based on what we have so far? Based on what we have, is 50-50 a better model or 60-40 a better model? Any thought? (60-40), we see two 60-40. Is there any, does anyone favor 50-50? That's probably more intuitive, but in this particular case, we only have these three events, okay? This is the fact. This is the fact that we collect. And our second model, our 60-40 model, say that the probability, if you believe it is right, if you believe your 60-40 model is right, then it tell you, hey, we have 14.4% probability to see this, which is higher than the 50-50 model. The 50-50 model only predict 12.5% probability to see the effect. So in a sense, whichever model predict higher probability that we see what we see, that's a better model. because we're scientists, right? We're supposed to respect the fact, right? So if this is the only piece of information that we have, then between the two models, the second one predict higher probability that we see the outcome, so it is a better model. Oops. So what is the best probability from this data set? We did see that the 60-40 is better than 50-50, but what will be the best probability or best model? It will actually be 2/3, and then 70-30 I think 70-30 will be better than 60-40, but to be more precise, it will be 2/3 and 1/3. 2/3 probability head and 1/3 probability tail. Essentially, that's just the average of the data. Well, so once we understand how model works, we'll like to find the best model. I kind of just told you that this will be the best model. I didn't really prove it. So how do we prove that the 2/3, 1/3 is the best model that we get to explain that data? Well, that's something called maximal likelihood estimate. So we know that I should probably have mentioned this terminology already. So the probability, I do see a question there. I will get back to your question soon. So the probability we got there is called the likelihood. It's called the likelihood. And this is our model. And the probability that your model to predict that a data happens, that's a likelihood. That's a likelihood. Of course, I'm gonna put it into a more general context, but you have a model and the probability that your model say, hey, how likely you're gonna see this data, that's a likelihood. That's a likelihood. And to figure out that 2/3, 1/3, the process, I didn't really describe this process, but there's a process to figure out that 2/3, 1/3 is the best probability among all. That's a so-called maximal likelihood. We want to maximize the likelihood. So it's called a maximal likelihood estimate. So the way I didn't really describe that process, but because the data here, a simple observation is because in the data, we have 2/3 of them head and 1/3. So whatever give you the mean, it will be the best probability. If you're interested in the mathematical proof, I could provide you offline. All right. So that's a little part. I need you to trust me on that. Okay. So how do we actually do that? In general, that's a so-called maximal likelihood estimate, which is a widely applied process. And then what if we care more than the 3 events? So some of you might think, even though it's 50-50, we might still end up with head, tail, head, right? So that data set of free flipping might not be that sufficient for us to make a conclusion, which is correct. So in many cases, when we train a model, when we try to conclude what the best model should be, we try to learn as much as possible from a data set, from your data, but still try to keep your model as general as possible. So we do have a data set with head, tail, and head. How much we would like to rely on that? Is it a good idea that we don't just go all the way to fit perfect on this data set? Well, in some cases, that's true. And that's a very important topic called the bias variance trade-off that is beyond the scope of the discussion today. And can we change the conditions? So from the discussion before, what I changed is the probability, whether it's 50-50 or 60-40. Is there anything else that we could change? And the answer is yes. In a more general situation, there are a lot of things that we could do to a model. And what I showed you before is probably an oversimplified situation. But all these together is how we could figure out the model, how we could optimize our model, as a terminology that people usually use. But that's for the future if you're interested in machine learning. But the main concept I would like to describe here is how how different models give us different likelihood. 50-50 give us 12.5, 60-40 give us 14.4. So that's model and likelihood, model and likelihood. So your model give you the probability of individual event. The likelihood is really the product of them. The probability of all of them happen. Any questions so far? All right. So once we understand this very simple situation, I want to make it a little bit more complicated. I want to put it into a real classification context. Well, I call it real. It's the data set I use is actually a simulated data set, so it's not a real data. But let me explain what I want to do here. So let's say we are I wonder if people could see this clearly. Let me make it a bit bigger. So let's say we are a company which provides certain kind of service, okay? And then we would like to survey people's or our customers' experience. So we allow them to rate our service, and the range of the rating is from -2 to 2. And you can see that this is not a real data set, because a real person would not rate something like -1.86, so many decimal places. Excuse me. So this is a simulated data set, a data set that I generated randomly. But hopefully this data set can help us to understand the type of problem. So we let the user rate our service. If it's very negative, that means they didn't have a good experience with us. So most likely they will not return. They will not return and use our service again. If they are very, very positive, it gives us close to +2. And then of course, people with more positive experience are likely to come back. And if we visualize the situation, so the x-axis that we see here, that's a rating that our customers give us. And then if a customer doesn't come back, then we use blue, or label it as 0, negative. A user doesn't come back. And if a user comes back, then we just use a red point to label, or label them by 1, or mark with a red point. And as I described before, right? If a user has a good experience, then most likely they will come back. So people who give us rating more than 1, it seems that all of them come back. Okay. And if a user who doesn't really like us after they try, right? They give us negative feedback and then they wouldn't come back. So this part is pretty easy. This part might also be pretty easy. But in between we see in this range, we do have some customer come back and some customer just leave, right? And we would like to come up with a reasonable model to describe this trend, And if you think about what kind of model would make sense, well, a typical logistic regression probabilistic model would be like this. Let me restart. A typical model will be like this, right? So if you have never learned logistic regression, you don't have to worry about how it is constructed. By the way, I usually don't have such a long hair, but because of pandemic, I'm very reluctant to to cut my hair. So sorry if this bother you. It kind of bothered me already. Sorry about that. So if you don't know logistic regression, it's okay. You don't know the mathematics formula behind it, that's totally fine. Just keep in mind what it does, what it tells us. Okay, so usually logistic regression will give you a curve like this, which represent the probability that the customer come back. Okay, so if you look at this particular customer, right, because the customer give us rating that is pretty good, so our logistic regression, from now on, I'm going to call it logistic regression. You could just take it for this curve. So our logistic regression predict a very high probability, more than 95% probability that the user will come back. Okay, so that's the height of logistic regression. And for a customer like this, who gave us a rating close to 0, so that's not great. So your model will predict lower probability, right? The height is that, a lower probability that the user will come back. And if a user even give us a negative probability, that's a negative rating, then the probability that he or she comes back is even lower. And the probability that the customer doesn't come back will be much higher. It's more than 86% probability. And of course, if the rating is even lower, then it's almost for sure that a customer wouldn't come back. So this is how logistic regression work. Any question about this? Great. And logistic regression, when I say logistic, so in the previous case, right, we have model, and the model predict the probability that individual event happens, and this is what happened here as well. So from the data set, we know that this person came back, and then our model should tell us how likely this person come back. Right, and if you have a customer who doesn't come back, you want your model to predict how likely this person come back. So logistic regression could be used for more than 2 outcomes, and this one I just want to keep it simple. So if you want to go beyond 2 possible outcomes, there are a couple of different ways that you could handle that. You could either go with there's certain method called 1 versus all, 1 versus 1 strategies that you could use, or you could just go ahead, try the cross entropy. Instead of use a likelihood function, go with the cross entropy. So that's that. All right, so that's logistic regression. It predict the probability of individual event for us, just like what we did before with that 50-50, 60-40. And with the with the example I gave you before, we know that we could change the prediction of individual event. It doesn't need to be 50-50, all right? We might want to change it to 60-40. For logistic regression, in fact, for a lot of different models, when you like to change your model, you change your parameters of your model, or coefficients of your models. Okay, so with logistic regression, we have a slope and intercept. You don't have to worry about what they are. Just keep in mind, if you are using different slope or intercept, you're going to have a different model. You're going to have a different model. So let's try. Previously, we have slope equals to 3. I should probably highlight that. We had the slope. This is a model characterized by slope equals to 3 and intercept equals 0. If we change these coefficients, slope equals 20 and intercept, I still keep intercept 0, okay? The model will become this. When you change the slope, if you use a bigger slope, then your logistic regression will raise much faster than a smaller slope. Okay, so that's how the slope work. And then you could also change the intercept. For example, if you use 10, if you slope equals to 10, then 10 is probably a bit too small. Let me use 20 instead. You can see that the rising part was moved to the left. if you use a positive intercept compared to intercept equals 0. And then if you use a negative intercept, then the rising power will be moved to the right. Okay. So this is how we could adjust our model. In a sense, this gives us the flexibility to choose different model. And we would like to know which model is better, right? We'd like to know which model is better. So let me go back to the example where slope equals 20 and intercept equals to 0. Negative 0, 0 is 0. Okay, that's fine. So our model is here. And let me see. I did check this point with the first model, slope equals to 3 model. Let's check the same point for the slope equals to 20 model. This model gives us the probability 98.43%, 98.43%. Okay, which is obviously, if you change your model, you change your prediction on the individual event. So the probability that your models predict on the same event, this one, who gave us about 0.2 rating, the two models predict different probability that they will come back. And this one is another. Did I check this one? Okay, maybe this one. Okay, so this is another point, another point that I checked before, right? If you look at this person, the first model predict less than 87% probability that a customer will come back. But the second sorry, 1, 2, 3, 4, the fourth one. Okay, so 1, 2, 3, 4. This is the one. So this model predict 100% that this customer will come back. All right, just based on these two events, let's say if we only consider these two events, I want people vote, okay? If you believe that the first model is a better model, according to these two events only, okay? If you think the first model is better, could you type a 1 in the chat? If you think the second model is better, could you type a 2 in the chat? Okay. So based on the two events that we check here, which one is a better model? 2, I see 1, 2. Okay, David say 2. I know that David knows logistic regression already, likelihood function already. So that's the correct answer. Again, as what we discussed before, whichever model that predict higher probability to see the events that we see, that's a better model. And if we only consider these two events, the second model the second models are almost for sure that the two customers will act the way, the way they act. So just based on these two events, the second model is way more certain than the first model. It's a better model. However, if we don't want to just make a judgment based on individual events, right? We'd like to be able to take the whole data set into account. So we want to know overall, not only based on the two events, but all the observations we have in the data set, which one is better. So before we do that, I wonder if anyone can point out a point. The first model does better than the second model. Do we have any example or any observation on this data set where the first model actually make a better prediction than the second one? First red to the left, let's see. So like this one, the first red to the left. So let's see. So for the left, oh, the first one, okay, I see. And this one, okay. So the first model predict low probability that that this customer will come back. Okay, so it predict like a 6% probability that this person will come back. However, the second model predict almost 0%, so I might not even be able to see that. Okay, I can't even hover through it. Right, and the right blue point that would also be correct. So if you just compare these 2 points, This one predict at least some probability that the person will come back, and the person eventually came back. But the second model predicted, no, it's unlikely. I don't believe that this person will come back. But the person, so the second one make even more mistake than the first one. So that's what happened to the individual event. For some observation, the second model is better. For some observation, the first model is better. So we need to somehow aggregate the performance on all the events. And how do we do that? This is exactly what I tried to show you before, right? Your model tells you how likely an individual event happens. So your model say there's a 60% probability that this event happened. There's a 40% probability that this event happened. There's 60% probability that this event happened. So the probability that all of them happen is the product of them. Now, just with the same concept, right? Our model said there is 99.75% probability that this event happened. And then 98% probability that this event, of course, we have to apply to all of them. And then there is 95.7% probability that this happened. And 98% that this happened. So all we want to do is to multiply all these probability together. That's the likelihood that our model achieve. That's the likelihood our model achieve. The overall probability, the probability that we see this data set based on our understanding on the individual event. So the mathematical formula for the likelihood function is really just this, or this is probably what you will see most often. So for all those customers who return, so this pi here means multiply all of them together. Okay, it's really just multiply all of them together. So for all the customer who came back, we multiply the probability that our model predict that the customer will come back. And for all the customers who left, we multiply the probability that the model predict that the customer will leave. And we just multiply all of them together. This is a likelihood function. And the whole process is really just the flipping coin process that I showed you before. But the main difference is that for the flipping coin, all the flipping enjoy the same probability of head or tail. But with the modeling, each observation might have different probability to return or to leave. So that's a likelihood function. And whichever model that predict the higher likelihood, that's a better model. That's essentially how this is really how we evaluate our model whenever we need to. Okay, there are different situations where we would like to evaluate our model for different purpose in likelihood function, or more generally the cross entropy type of quantity. They are the most commonly used one. Well, before I talk about or add up other details, I wonder if there's any question about likelihood function so far. I hope I have put it in a simple enough way. Even you don't know the mathematics behind the likelihood function, you sort of understand what it is about. And it's really just aggregated the probability of individual event. Yep. I like this example a lot. I like to compare these examples a lot because, again, science is no magic. Mathematics is no magic. So people feel that mathematics is very difficult because usually they look at the formula instead of the connection with our everyday thinking. So gradually, science look more and more like magic. If you have watched the Iron Man, I think it's Iron Man 3, when Tony Stark gets some object from his father's legacy object and try to figure out new material for his for his battery or whatever you call it, right? He was sitting there thinking, and then all those circuits and a diagram flowed around him, and suddenly something clicked in his mind, and he was like, "Ha!" And then I really don't see the difference from that. You know, if this is how people perceive science nowadays, I really don't see the difference between that and, say, Doctor Strange, who is a wizard in that franchise. But really, mathematics or science, there's no magic. There's always something brute in our everyday thinking that that we could have a reference from. Okay. Right. I'm sorry. I kind of hear some background noise. I wonder if there's any questions or. All right. So there's a question in the chat. I can see a question in the chat right now. So to determine which model is better based on historical data, which is true and false, that what I show you is just one way to evaluate your model. In fact, that is the very first. That's how we evaluate a model at the very beginning stage. Later, we probably want to do cross-validation, we want to have a test data set, we want to retrain our model. What I described to you is really so-called training process. When we begin to build our model, it's a bit like the practice exam for the student. The goal of the practice exam is not to, kind of score this student. It's more of helping the student to learn. And that is, and very often when you're learning, you also want to know how much you improve step by step, right? So that's a very frequent evaluation. This is what I have shown you. And of course, if you always evaluate you wouldn't always evaluate your student with practice exam. You have to let them to take the real exam, or eventually take the entrance exam to a college or interview to a job, right? That's for later. But what you say here is kind of correct, that evaluation on model always depends on historical data set. You could use a historical data differently, but if this is only thing that we know, we could only work on based on the data we have. All right. Any other questions or comments? Okay. If not, I think I have another 10 minutes. We scheduled to end at 3. So just for people who know the likelihood function already, very often people introduce a likelihood function in the context of classification problem, just like what I did. But in fact, a likelihood function could be applied to a regression problem as well. So this is, again, for people who already are familiar with likelihood function and regression problem. So I just want to quickly show you a typical regression problems is when we want to predict not only 0 or 1, but the value in betweens are also possible, right? So we would like to predict some continuous value. In the previous situation, we only want to, in a sense, we want to predict whether it's 0 or 1, nothing in between. But for regression problem, we could have very flexible y. And now we want to predict the y value. And a very, probably the simplest model that we could have is a linear regression model. Very often it is represented by a straight regression line like what we see here, okay? But how do we get the probability or likelihood from this kind of model? So, okay. So with a regression problem, because we are predicting numerical outcome, we no longer can talk about the probability. We have to talk about the probability density. If you're familiar with the normal distribution, the height of your bell curve, that's probability density. And we're going to just use the bell curve to predict the likelihood. So for this particular point, it is so far away, right? The distance from the point to your prediction is this. And then the likelihood that we have such a distance is 0.1728. That's a probability density. For a point that is closer to the regression line, it enjoys a higher probability density. This is more than 0.35, right? For a point that is further away, okay, it will be lower than the 17 that we have before. So the further one is less likely, the closer one is more likely. And then again, the model gives us it's not a probability, but a probability density. It gives us the probability density of an individual event. Then the overall probability is again, the overall likelihood is again the product of all the probability density. So you will see that this concept is very general, all the way from a very simple binary logistic regression to neural network. Even you go with more sophisticated model, you use the same concept of likelihood. And even you want to work with a regression problem, the way we construct likelihood from an individual probability density is the same. What do you mean by the different event? So here, when I say event, each event is an observation that we have in a data set. So here we have one event, here, 1 point, another event, another event, another event. Each of them is playing the role of one flipping of a coin. Yeah, it's a different situation. This is a regression problem. What we try to predict is a number instead of just 0 or 1. All right, I do see Manisa's message. So I guess I wonder, Manisa or Vivian, do you have anything else that you would like to add?
No, I'm good. Thank you so much, Luke. I enjoy your session.
Okay, great. So if you have any more questions, then I'll be happy to answer it. I'll stay here for a few more minutes and answer it. Otherwise, that's it. That's everything I have for today. Thank you.
Thank you so
very
much, everyone, for joining our event. Hope you had a good time. Any further comments and questions? Awesome. So we run regular events every week. Please follow up on our linking page to get information about the next event. Hope to see you guys in the future events. Yes, we're gonna do the recording. So the best way to get our recording is to go to our main website, nycdatascience.com, and scroll down to the bottom of the newsletter sign up. Please make sure you sign up to our newsletter. We also send out weekly newsletters. Okay, I'm gonna wrap up and thank you everyone for attending. Thank you, Luke, for hosting. Okay, bye.